And now, coming to you live from a fantastic viewpoint of my neighbor's mossy rooftop, Pre-Calculus Math 11. Dance. Dance. Wash your hands for 20 seconds, like the length of this intro. Today, solving rational equations. Alright, hey guys, nice to have you here, nice to see you. Let's take a look at methods for solving rational equations. So we've got this nice equation here, 3 over w minus 4 equals w plus 1 over 2. And we want to look at first doing a graphical solution and second doing a algebraic solution. So to do this graphically, we'll get our calculators out. You can see I've got these previous equations here from the absolute value lesson. Sometimes I don't want to get rid of an equation. I want to keep it around. I just don't want it to show up on the graph. So what you do, like I just did, is click to the left so your cursor is on the equals sign, press enter, and now that equation is deselected. It no longer graphs. You can see it just got taken out of the table of values and the graph window to the right there, showing all three components of my screen at the same time. So I'll deselect the second equation and I'm going to go down to y3 and I'll graph this equation here. We have two methods for graphing, just like we had for graphing and solving with quadratic equations. One method is to put everything on one side of the equals sign, and the other method is to use the left side and the right side as separate equations and graph them and then find where they intersect. It doesn't matter to me which one you do, just choose one. So I will go with left side 3 over, we can't use w, x minus 4. Let's look at doing this with left side equal to right side. And so we will go x, oops, I didn't choose. We will go x plus 1 over 2. So when I go to graph this, I want to look at where these two equations intersect, and I'll find those points of intersection. There they are. How do we find the points of intersection? Again, we go into this calculate menu. The fifth item down is intersect. And so our first curve is y3, that's good. Our second curve is y4, that's good. I guess I want to move it close to this point of intersection. So come back to around here, negative 2.4. Turns out it's exactly at negative 2. To get the second value, same thing. Repeat that process. First curve, second curve. My guess, I don't know, it's over here somewhere. That looks close to 5. Rather than pressing this arrow and clicking until it gets all the way over there and taking a bunch of time, I can actually just type 5 and press enter. Oh, look at that. The intersection is actually 5. It's almost like I knew that in advance. If it hadn't been 5 though, still you can type that value in and just get it closer to that point of intersection just with one keystroke. Okay. Back to solving this as a single equation, I guess what I would do differently then is have the equation be y equals 3 over x minus 4 and go minus the second term, which is now x plus 1 all over 2, and we can graph that whole thing now. And we see it going through here. It looks very different than what we just saw with the two previous equations that we graphed, right? And we'll get into properties of these equations in a later course. For right now, we're just looking at solving them. So now, because I have it all as one equation, I'm not looking for an intersection. I am looking for the 0. And we have to do the same game that we did with quadratics on solving them. So go to a left bound, somewhere to the left of negative 2, a right bound, somewhere to the right of negative 2, a guess. Turns out it is negative 2. Shocking. It's almost like we already knew that. And then repeat that same process over to the other side. Calculate the 0. Left bound, now I want it over here closer to 5, so I'll type in left bound of 4, and right bound, I'm not going to click to it. I'm just going to type in 6, and I'll make my guess 4.5. But it still knew the 0 was at 5. Isn't that amazing? And now let's take a look here on Desmos. How would we do this over here? Again, if you try to graph this using W as the variable, even though that's what's in the original equation, you're going to get this error message. We only support implicit equations of x and y. You can't graph a W equation. It doesn't work. If you try to graph the original equation, you're going to get this with these two vertical lines here, which we now already know are at 5 and -2. But this isn't really a good method because when you go on here, you can't click. You can't get any values off of this graph. Nothing reads nicely. I think it's 5 and -2, but how do I know it's not 4.9? Right? So this is not a good way to graph this one. I'm going to get rid of it, get rid of that as well. So we could do it the way we did originally on the TI, which is graph the left side and the right side, and we see those two equations. And again, what I love with Desmos, you come over here and you click, and you come over here and you click. It's already got points at interesting places, right? The y-intercept is interesting, not for this question, but it is an interesting place in general. But what we've got is here this intersection point when x is -2, and at this intersection point when x is 5. It turns out that both of the original equations there, the left side and the right side, come to a value of either -0.5 or a value of 3 for those two x values. Going to the other method we looked at, just graphing it all as one equation, then you get again these points that are interesting highlighted for you on the screen here, and we get these two 0 values for the equation where x is -2 and where x is 5. So that's how you do this graphically, all 4 methods on both different platforms. Now we will look at an algebraic solution for this same equation. So now to solve this algebraically, there are 6 steps here that we need to keep in mind. The first step, factor your denominator if possible. We have w minus 4 and 2. You can't factor that. Identify the restrictions on the variable. Sure, we can see very clearly that w must not be allowed to equal 4. Step 3, identify what the LCD, the lowest common denominator of all the terms, would be. Well, we just have these 2 terms here, and so clearly the lowest common denominator, new pen color, is going to have to be 2 times w minus 4, and I'm just going to leave it in the factored form. Now that we have the LCD, we just go ahead and we multiply the entire equation, both sides, by the LCD. So this looks like 2 times w minus 4 times 3 over w, that's not a w, 3 over w minus 4 equal to w plus 1 over 2, also multiplying the LCD, which is 2 times w minus 4. And so we have this multiplication here. We cancel things off because it's going to work out nicely. Look at this. On the left side, w minus 4 cancels with w minus 4. We're left with 2 times 3, which is 6. And over here, the 2 cancels with the 2. We're left with w plus 1 times w minus 4. Hey guys, can we just pause here for a moment and talk about something? There is this thing that I hear so many of you use all the time, this phrase, this term, cross multiplication. Can we just have a moment to talk about what cross multiplication is and what it isn't, when you can do it and when you cannot do it? In this question here, cross multiplication would work. You could simply do 3 times 2 equal to w plus 1 times w minus 4. And in fact, that's what happened when you look down at the second line of working right here. We've got 3 times 2 is 6, w plus 1 times w minus 4. So you could have actually just gone straight to that point here by doing cross multiplication. But what is cross multiplication? Well, what it is multiplying the entire thing by the LCD. That's what we did, and we resulted in this stage where it looked like just cross multiplication. So that's why it works. It works because it's a specific case of multiply by the LCD. When does it not work? It doesn't work if you have an equation with more than two terms. If there was a third term on here, if the right-hand side said w plus 1 over 2, and then right beside it, it said plus 4, then you could not do cross multiplication. You would have to multiply each of the three parts of the equation by the LCD. So just be careful that you can do cross multiplication, but you may only do it when you have an equation of one fraction equal to one fraction. There cannot be a second or a third term beyond each of those fractions on either side. Okay? All right, back to it. And step 5 says solve that resulting equation, whether it's linear or quadratic. So I'll scroll down and do some more working on this. So we'll have 6 equal to, if we expand this out, we're going to get w squared minus 4w and plus 1w, so that's minus 3w and then minus 4. Solve a quadratic equation. If you don't know how to do that yet, see chapter 4. Minus 3w minus 10. We could solve this by graphing. We could solve this by factoring. We could solve this by completing the square. We could solve this by quadratic formula. You know which one to do. W minus 5 and w plus 2 are going to work out to this, which gives me two solutions here, either that w is equal to 5 or that w is equal to negative 2. The final step that we have to do here is just to check these solutions. You need to check them against the restrictions, which we're okay with. Our restriction was w cannot equal 4. We don't have that. But of course, we should also check them just to make sure that our math actually worked. So you could do this manually, or you could throw it back into the calculator, and I'll show you how to do both of those right now. All right, so that has been a quick primer on how to solve rational equations. Things that could be different, of course, you might have more than just two terms in the entire equation, and so you could have more things there to look out for in terms of the LCD. You could have an LCD, you could have denominators in the first place that need some factoring. And of course, you could have something that when it gets to this quadratic stage doesn't factor nicely, maybe needs to be solved with the quadratic formula in order to get the exact values of the solutions there. Okay, hopefully that helps. If you've got any questions, hit me up in the Google chat. And until next time, keep your pencils sharp, and I'll see you online. Bye.